Okay, let me continue with some one application. Before going to the next section, let me continue with one application of this AR duality. So application is the following Morita type theorem. So as appeared in the first the introduction part of Yama-sensei's talk, we had some equivalence between the singularity category or some cluster categories, and we can somehow this suggests that we can somehow model the singularity categories as by using the cluster categories. And so this example was something most fundamental examples, but this suggests that we can perhaps get an understanding of for general O by using some much more complicated finite dimensional algebra, and our Morita theorem is exactly what it does. So let me look at the theorem. Yes, state the theorem. Yes, and let's consider the commutative case for simplicity. Yes, RP positively graded. Commutative Gorenstein ring of dimension D, such that degree 0 part has finite global dimension. In the commutative case, it just means that it is a field, and isolated singularity, again for simplicity. And of Gorenstein parameter P. And I assume this is non-zero. Yes. And suppose, as in the previous talk, we have as equivalence between the graded singularity category and some perfect derived category of some finite dimensional algebra A. Yes. Then what we can do is to from this equivalence, we can construct automatically deduce a triangle equivalence between the Z mod PZ graded singularity category and the D-1 cluster category of A, which is by definition the perfect derived category modulo the cell functors. Yes. Shifted cell functor. I take the triangulated tau. Minus D-1. And the ungraded singularity category would be some Z mod P quotient of it. Yes. Yes, so F is a pth root of this functor in the sense that pth power of F is isomorphic to this tensor functor. Yes. And yes, it is, I think it is not possible to somehow deduce these equivalents only by looking at triangulated categories. And what is essential is that this has a this right Calabi-Yau property. Yes, right Calabi-Yau. And in other words, if we have certain right Calabi-Yau property, we can generalize this kind of this implication to various kinds of not necessarily commutative Gorenstein, but various kinds of Gorenstein rings satisfying this. equivalences. So our next aim is to extend these Calabi-Yau properties to much more general classes of algebras. And this is the main aim. And for simplicity, I will focus mainly on finite dimensional algebras. Okay, so yeah, as we saw before, something like the pre-projective algebra of thinking type. And yes, but finite dimensional algebras are a bit somehow too small, and we will look at more general class of certain DG algebras. Okay, let A be a DG algebra, and I will like to introduce some classes of DG algebras that behave quite closely to the ordinary finite dimensional algebras. Yes. So first of all, a DG algebra A is called proper if the total cohomology of A is finite dimensional. So more precisely, I should say it is proper over K. But anyway, so this is a direct analog of finite dimensionality. And also A is called connective if it has no positive cohomologies. So this is equivalent to, saying that A itself in the perfect derived category is a silting object. And a proper, yes, so assume that A is proper and Gorenstein, proper and proper DG algebra. A is called Gorenstein. If the sixth subcategory that A generates in the derived category coincides with the sixth subcategory the duo of A generates in the derived category. Yes, so it is a natural analog of Iwanaga-Gorenstein property of finite dimensional algebras. And we need to introduce one notation, and I will denote by PVD of A the object in the derived category of A such that it is perfect, considered as as the DG module over K, or in other words, just a complex. So it is equivalent to saying that the total cohomology of X is finite dimensional, and it is called the perfectly valued derived category of A. So for example, if A is an ordinary finite dimensional algebra, then this PVD of A is exactly the bounded derived category of finitely generated modules. Okay. Yes. And now this kind of consideration allows us to define the singularity categories for proper DG algebras. So in a very natural way, the singularity category of a proper DG algebra A is by definition the perfectly valued derived category modulo a perfect derived category. And it is again denoted by SG of A. And the goal is, as I said, goal is to discuss the write the Calabi-Yau properties. of the DG enhancement of this singularity category for, let's see, let me write it lambda, or lambda mainly proper connective and Gorenstein DG algebras. Okay. And mainly I will be interested in positive T, but anyway. Okay, so I would like to introduce several more notions. So, yeah, I will need to define what the bimodule dual. Yes, for bimodule M over a DG algebra A, DG A bimodule, we defined the bimodule dual as the dual over the enveloping algebra. So this is object in the, so if we take the dual to the ring, it will become the object in the opposite side. But because the enveloping algebra and its opposite are isomorphic, yes, by switching the components up to sign, yes, this will become again an object in the same derived category. Yes, and I would put it in check and call it the bimodule dual. And in particular, for the bimodule dual of the ring itself is called, yes, is called the inverse dualizing bimodule. And I will give a quick remark that this bimodule dual is a certain Kyushu dual to the ordinary K dual. So yes, as we have seen that the ordinary K dual of A represents the cell functor in the perfect derived category. Yes. And in the same way, this bimodule dual represents the cell functor in the perfectly valued derived category. Yes, as I forgot to mention, this is the Kyushu dual to the perfect derived category. Yes. And yeah, so in this way, so this seemingly complicated object is a way to another way of encoding certain duality. Yes. Okay. Okay, now we can state our first result by myself and Art Keller. And so let lambda be a proper connective DG algebra, Gorenstein DG algebra. If lambda, if the inverse dualizing bimodule of lambda shifted by d+1 and the identity bimodule lambda is isomorphic in the singularity category of bimodules, then the DG singularity category is right, the Calabi-Yau. So this is our first result. Okay, so for example, if lambda is a symmetric, ordinary symmetric algebra, then we have that lambda check and lambda isomorphic already in the module category, or in other words, already in the derived category. So in particular in the singularity category. Yes. So this implies that the DG singularity category is -1 Calabi-Yau. Yeah. Which is also a special case of the previous theorem for R equals K in dimension 0 case. Yes. So, and so this is a first example, and this kind of isomorphism in the singularity category already appears in some previous works. So, for example, consider the pre-projective algebra of thinking type. Then lambda check shifted by 3 is isomorphic to lambda in the singularity category of bimodules. And this can be seen as a direct computation of the bimodule resolution of lambda. And more generally, there's a higher version of this result, namely by consider the n+1 pre-projective algebra of n representation finite algebras. Then this bimodule duo shifted by n+2 is isomorphic to the identity bimodule in the singularity category of bimodules. This is due to Claire Amiot and Stefan Oppermann. So this by this theorem, we see that the DG singularity category of this higher pre-projective algebra is n+1 Calabi-Yau. Yes, this already appears in can be seen by several other results, but this is one of our explanation. And let me give some comment about how these things can be proved. So as I mentioned, these kind of things can be interpreted in terms of offshoot homology stuffs. So we should look at where these morphisms live. And so we consider the home space in the singularity category shifted by d+1 to lambda. And we can show that this is isomorphic to the d+1st offshoot homology of the DG singularity category of lambda. This is somehow relatively easy, but in fact, this can be seen as, again, by certain Cauchy duality that this is isomorphic to the duo of the -d offshoot homology of the DG singularity category. Yes. And this was where the right Calabi-Yau structure lives. Right, weak right Calabi-Yau structure. And what we show is that the isomorphism here, isomorphism here corresponds to this isomorphism here. Yes. And this is how what we do. Yeah. Yes. And okay. So the next question is how to produce DG algebra satisfying this kind of, certain Calabi-Yau property. And towards the end, I would like to present some systematic construction. And for this, we need to introduce some several other concepts, like what is called left Calabi-Yau structures. Yes. Okay, so let me start from some other notions. So about smoothness of DG categories. Okay, DG algebra A is called smooth. if it is perfect as a bimodule. Yes. So for example, if A is an ordinary finite dimensional algebra, then A is smooth as a DG algebra if and only if it has finite global dimension. Because we assume that our base field is perfect, and yeah. So in this sense, this smoothness is an analog of finiteness of global dimension. And then left Calabi-Yau structure. Again, I will say weak today. Left Calabi-Yau, left and Calabi-Yau structure on a smooth DG category, smooth DG algebra. A is an isomorphism from the n-shifted inverse dualizing bimodule to the identity bimodule in the derived category of bimodules. Yes. So again, so what this weak means is that it comes from Hochschild things. So this morphism space lives in the, this morphism lives in the space like this from HX to A, and by, yes, ordinary adjunction, this is H minus N of A tensor A E double bimodule dual by smoothness, and this is, yeah, nothing, H minus N of the bimodule dual. Yes, the bimodule, double bimodule dual is isomorphic to itself by smoothness, and this is exactly the nth Hochschild homology. And the weak left Calabi-Yau structure lives in the Hochschild homology, and the strong left Calabi-Yau structure lives in so-called negative cyclic homology. Yes. Yes. Okay. Okay. This is just a side remark, and yes. Let's see. So as I said, this bimodule dual is the Cauchy dual to the ordinary K dual, and this is justified by the following proposition. If you have a smooth DG algebra, and then for each perfectly valued A module, we have a duality from X to Y. Dual is isomorphic to the R-hom of A from Y tensor A check to X. So it means that on the perfectly valued derived category, this functor gives the inverse of the cell functor, and this is why it is called the inverse dualizing bimodule. And in particular, if A is left and Calabi-Yau, then its perfectly valued derived category is an n Calabi-Yau triangulated category. So this also justifies certain duality, Cauchy duality. I see a comment in the chat. In the comment, the rightmost term should be DHH minus D of the Cauchy dual of DSG lambda not. Let's see. You mean this part? In the comment, the rightmost term should be DH Cauchy. No, it's somehow a DG singularity category is somehow self-Cauchy dual. Yes. So we have that per lambda and PVD lambda and SG DG lambda, Yes, so these two are Koshu-dual to each other, and this Koshu duality somehow is the self-Koshu dual of this DG singularity category. Yes, so this is the point, and yeah, this is what this explains. And yeah, so this is correct, not the Koshu dual of the DG singularity category. Does it answer your comments? Yes, yeah. Yes, so yeah, this is itself. Okay. Okay, so yeah, so this yeah, so yeah, if we have a left Calabi-Yau algebra, then its PVD is n Calabi-Yau, just like if we have a right n Calabi-Yau, then its perfect derived category is Calabi-Yau and it's Koshu dual. Yes. Okay, so so yeah, we introduced left Calabi-Yau structure, and there's a somehow universal way of constructing left Calabi-Yau structures, namely the Calabi-Yau completions, or in other words, derived pre-projective algebras. Okay, so let me briefly go on to the definition theorem due to Bernhard Keller. So if we start from arbitrarily smooth DG algebra, and for each integer n, the derived pre-projective algebra, derived n pre-projective algebra, or the other terminology is the n Calabi-Yau completion, is the derived tensor algebra of the n-1 shifted inverse dualizing bimodule. Yes, or more precisely, it is a tensor algebra of cofibrant resolution of this shifted inverse dualizing bimodule. Yes. Yes. So this cofibrant resolution means it is an analog of projective resolution for ordinary algebras. And it is denoted by pi n of a. Yes. And then, yes, so this is the definition part, and the theorem part is that, yeah, this pi n a is indeed left n Calabi-Yau. So this is a very somehow abstract definition, and we can, but in fact, we can describe it in terms of quivers and relations quite explicitly. So let me consider the somehow special case. So let A be a path algebra of finite quiver Q. And let me just focus on n equals 2. So consider, for example, the quiver like this, type A2 tilde quiver. Then we consider its the quiver Q tilde, yes, which is obtained by adding the dual arrows yes, in degree 0. And several other loops. In degree -1. And we declare the differential of these loops to be the commutator. Yes. So at T1, it becomes what it is. minus AA star minus C star C. The sign doesn't really matter, but AA star minus BB star and DT3 is I don't know, CC star plus B star B, I think. Let's see, minus, no, BB star. Maybe this should be, DT2 should be B star. So it should be minus, I guess. Yes, I think this is correct. Yes, and yeah, whatever it is. So yes, this pi 2 of this KQ is the DG path algebra of this quiver Q tilde and with this differential. Yes. Yes. So what it says that if Q is Dinkin, whether or not for arbitrary quiver Q, we see that this H0 of pi 2 KQ is the ordinary projective algebra. Because these differentials contribute to pre-projective relations. And so we have a quotient map from pi 2 KQ. And so this is, yeah. And what we know is for if Q is Dinkin, then H0 is finite dimensional, but the total cohomology of pi is not finite dimensional. And if Q is non-Dinkin, then this pi to H0 is a quasi-isomorphism. So yes, so as I mentioned in the beginning, this somehow answers the first question. Is we had this for non-Dinkin quiver, the derived category of finite length modules over H0 pi is 2 Calabi-Yau. This is because of the 2 Calabi-Yau property of the derived pre-projective algebra. And yes, and in this case, the derived category of finite length module is nothing but the PVD of this derived pi. And the reason that the H, for in the Dinkin case, it doesn't hold is because we are looking at different things. And if we consider the derived pi for Dinkin quivers, then the same holds. Yes. Okay. And so the remaining question is how to explain this H0, the singularity category being Calabi-Yau for Dinkin case. Okay, so let me go on to this one motivating result. Which is due to Brown, Yama, Wright, and Scott. So consider the ordinary pre-projective algebra of a quiver, which are denoted by gamma. Ordinary pre-projective algebra of a quiver Q, and let W be the Coxeter group of Q. Then the statement is that for each element in the Coxeter group, there is a nice, well-defined ideal denoted IW of gamma, which is called a tilting ideal, such that its quotient by this ideal is a finite dimensional one Iwanaga-Gorenstein algebra. And the singularity category of this Gorenstein algebra is a 2 Calabi-Yau triangulated category. And our second result is that we can generalize, or we can do something analogous to for left Calabi-Yau DG algebras. Yes, by myself and Claire. Yes, so let's start from pi, smooth left D Calabi-Yau DG algebra with positive D, and let I be a DG ideal such that, yes, we need something like the tilting ideal. So the condition would be the natural morphism from the pi to the derived endomorphism ring of I should be a quasi-isomorphism. Yes. And suppose that that the quotient of pi by this ideal denoted lambda is proper. This is for simplicity, but yeah, proper and connective. Then the statement is that lambda is d minus 1 Iwanaga-Gorenstein. Yeah, Gorenstein. In the sense that lambda is Gorenstein. So, and this d minus 1 means that its inverse realizing bimodule is concentrated in degree at most d minus 1. And the second statement is that lambda check shifted by d plus 1 is isomorphic to lambda in the singularity category of bimodules. And therefore, by our first result, this implies that the DG singularity category is right D Calabi-Yau. Okay, so this is the theorem, and let me give some examples. So, as I said, it's as in the motivating result. This is certainly an example. Yes, let pi be a pi 2 kq of a non-dinking quiver of a non-dinking quiver, and I to be the tilting ideal associated with each element of the Coxeter group. Then this implies that so we can certainly these assumptions are satisfied. So by theorem, we see that DG singularity category of this pi modulo IW is right to Calabi-Yau. Yes, which refines this Calabi-Yau property as a triangulated category. Okay, this is the zeros example, and we also consider the derived pre-projective algebra of Dinkin type, or so the point is that we can look at the ordinary pre-projective algebra of this Dinkin quiver as the ideal quotient of this derived pi by truncation at degree -1. And this ideal satisfies that, yes, it is, follows from some, elementary or some basic properties of cluster categories that the derived endomorphism ring of this truncation is by itself. So we can see that we can apply this theorem. So we see that pi 0 shifted by 3 is isomorphic to H0 pi. As in the classical theorem. So this DG singularity category would be right to Calabi-Yau. So the correct way of viewing this ordinary pi 0 is a ideal quotient of this derived pi, and that's the answer of why something I mentioned in the beginning. Okay, so there are several more answers to several more examples we can apply. So maybe some of you know that the paper entitled paper by Keller-Reiten entitled cluster tilted algebras are Gorenstein and stably Calabi-Yau. And stably Calabi-Yau. Yes, we can explain their main result from this theorem. So we start from a 3 Calabi-Yau DG algebra. Yes, let pi be a left 3 Calabi-Yau connective DG algebra with H0 pi being finite dimensional. And this H0 pi is exactly the cluster tilted algebras because it is nothing but the endomorphism ring of the initial cluster tilting object in the associated cluster category. Yes. Yes. And we can show that, again, we can view this H0 pi as the ideal quotient of this truncation. And because of the 3 Calabi-Yau property, yes, we can also show that, yes, it satisfies the same equality because of the, this dimension is just 3, yes, only 4, only up to dimension 3. So so then we can apply this this theorem to see that this is quotient is indeed Gorenstein, and this isomorphism, and in particular this right Calabi-Yau property. Yes, H0 pi is right 3 Calabi-Yau. And this enhances this stably Calabi-Yau part. Okay. And yes, I think I have 5 minutes or so left. So let me give some brief comment about how to how this some mention one structure behind this theorem. So comment behind. So yes, let me just say okay, and so I would like to say why this holds, and the point is that in fact what we have is that we have the morphism from pi to lambda. It's just a quotient map, has a relative left d+1 Calabi-Yau structure. So yeah, so what it means, yes, if you're familiar with relative Calabi-Yau structures, yes, yeah, you might guess, but yes, so just like this left Calabi-Yau property, yes, so this left Calabi-Yau structure was something isomorphism between some bimodule duo and the original one, and the relative thing, relative Calabi-Yau structure is an isomorphism of certain triangles. Yes, so we have the multiplication map and some cone. Yes, let's write it lambda omega. A triangle in the derived category of bimodules over lambda, obtained by extending this multiplication map, and we apply this bimodule duo over lambda, and what we get is that, yes, so first we visualize this thing, you get by junction this bimodule duo of pi, lambda, and omega duo shifted by d+1, and lambda duo shifted by d+1. And this relative Calabi-Yau structure is an isomorphism of triangles. Yes. Okay. Yes. So these are isomorphic because pi has a left d Calabi-Yau structure. And yes, and yeah, relative states is that these remaining things are also isomorphism. And so if we look at these triangles and we stare at this part. So because pi is smooth, we can see that this is, well, lambda tensor. Yes, so this is pi tensor pi e, that's a lambda e. And because pi is smooth, this is perfect as a bimodule over lambda, which means that this is an isomorphism in the singularity category. So by looking at this part, we deduce that lambda check shifted by d+1 is isomorphic to lambda in the singularity category of bimodules over lambda, and this is yeah, exactly what we wanted in the bimodules. Yeah, so yeah, I think this relative Calabi-Yau structure is rather new, and yeah, this is the point behind this result. And I think my time is just up, and I would like to stop here. And thank you very much for your attention.
Thank you very much for your very nice presentation. Okay, are there any questions?
Thank you for your talk. May I ask a question?
Yes.
Could you explain again the why the singular digit category is self-causative?
Yes. I think I should. So singularity category fits in the exact sequence of triangulated or DG categories. So we have this exact sequence of DG categories. And so so to explain this isomorphism, we should look at its Pochette homology. Yes, or yeah, let's look at the mixed complexes. Yes, the mixed complex of lambda. and mixed complex of lambda check, and mixed complex of DG singularity category. We can dualize this triangle. And so what we get is D of complex of Cauchy dual, and D of mixed complex of lambda, and D of mixed complex of singularity category shifted by 1. And these are isomorphic because of Cauchy duality. And this implies that this is also isomorphic. And taking the cohomology, we get this isomorphism. So in this sense, it is DG singularity category is somehow self-Cauchy dual.
Okay, thank you. I think okay, thank you.
Are there more questions or comments?
Could you say something about how to obtain the relative Calabi-Yau structure? How do you construct it?
Let's see. Let me recall. Yes. Yes, I think we needed certain connectivity of lambda in this setting, and let me remember. I think it was a truncation with respect to some T structure or something. Though, yes. Let me see. Yes. For example, in the for example, in this case, from the map from pi to a quotient pi tilting ideal, it's pi to pi w, let's say. We have this multiplication map and some mapping cocon and the dualized triangle. Yes, and yes, we can show that at least in this case, it was both are truncations of this middle term with respect to the standard T structure. Yes, so this in this case, this concentrates in degree 0, and this concentrates in some lower degree, and the same holds for these things.
Okay.
Yes. We use T structure. Yes.
Yeah, but how to get the vertical map?
Yes. In the case of yes. If both are truncations with respect to T structures, then we automatically get, because there's no map in this direction.
Oh, okay.
Yes.
So actually, you get a weak relative Calabi-Yau structure.
Actually, this we can lift it the strong one.
Oh, okay. Thank you. Oh, another thing is that but by the first question asked by Kai-Wang, you said you gave this diagram. Yeah, so I think this also holds for cluster category. So cluster category also.
Yes.
Okay,
yes.
Thank you.
Okay. Any other question? So if it is not the case, let's thank Norihiro and also all the speakers of today's session. Thank you very much. See you all tomorrow. Yes. Thank you.